Hey guys, today we're here to talk about one of our last applications of differential calculus, related rates. So I'm just going to take you back to one of the first things you guys did when we started calculus. So let's say we had our XY axis here, and we had, oh, pen problems again, a nice little function here. Let's make it a little bit thicker. Y is a function of x. Okay, what does it mean to talk about when we say f dash x or dy dx? What does that mean? Okay, there's a couple of ways we can say it. We know that talks about the rate of change. So we can say this is the rate of change of y. So how our variable y is changing with respect to x. So compared to how y is changing, we're looking at how y is changing compared to how is x changing. So when we look at tangents, we go back and have a look at what we started with, and we're looking at slope. And we're looking at how y is changing compared to how x is changing, delta y over delta x. Talking about the slope, the rate of change of y with respect to x. Of course, when we get into real life examples, we're often not talking about x and y. So let's say we had our axis, let's say we're measuring time in our x-axis. And let's say we're filling the swimming pool up at home, and we're measuring V for volume. That might be in cubic meters or litres. You know, we can define that in the specific question. So what would it mean here? So instead of saying y with respect to x, we now have what is changing? V is changing with respect to, not x anymore, but to t. This is saying how is the volume changing as our time is changing? How is the volume changing with respect to t? Okay, so what would our derivative look like there? We'd see something like this, dv dt, where our v is our volume and our t is time, whether that was seconds or minutes. Okay, so we're going to sort of expand our understanding of dy dx into sort of different examples where we're not looking at just y and x, abstract, functions. We're going to have a look at specific things where we're looking at real life phenomenon changing, and we're not just looking at x and y. So let's have a little bit of a look at that. All right, here's our first situation. Let's get a nice thin one here. All right, a plug was pulled out of a sink and the water is going down the drain. The volume V in millilitres, so we're given the units this time, after t seconds is given by. Okay, so we have a formula here, and it's saying that the volume is dependent on the time. Okay, so first thing I'm going to ask you is find dv dt. dv dt, well, if this was y equals 40 10 minus x squared, we'd call that dy dx. How does y change with respect to x? But of course we don't have x and y, we have t and v. So we're going to find dv dt using our skills of differentiation. Alright, dv dt. Alright, what do you want to do here? We could do a few things here. We could expand this, couldn't we? Let's do that. We've got 40 outside 100 minus 20t plus t squared, and let's neaten that off. What do we got? 4,000 minus 800t plus 40t squared. So there's our expression for v. Okay, I think we're ready to find dv dt now. So let's get that nice simple three-term polynomial. So let's go. Derivative of 4,000, that's a constant, it goes. Negative 800t, we'll have a negative 800 here. And 40t squared, let's use our power rule. 2 comes down the front, and we have plus 80t. So there's dv dt, but what does it mean? What is that really saying? What is it representing in this scenario? Well, we're looking at the rate of change of the volume of the sink with respect to time. In other words, how is the volume changing as time changes? Okay? All right. It says, what is the rate? We're after a rate, so this time we're definitely looking at our dv dt, our derivative. What is the rate at which the water is initially draining out of the sink? Okay, we've seen initially before. Initially, remember, means when t equals 0. Okay, so we want to find the rate of change of the volume when t equals 0. That's easy. We just put t as 0 into here. So we have, let's go over here. Pen problems. Goodness me. Let's make it a little bit thicker, see if that'll help. Alright, dv dt, when we put t as 0, we've got negative 800 plus 80 times 0, and we've got negative 800. Okay. And the last thing it says, what is the rate at which the water is draining after 10 seconds? So instead of initially, we want to have a look at the rate when t is 10. When t is 10. Okay, so let's find dv dt when t equals 10. So we've got negative 800 plus 80 times 10. We've got negative 800 plus 800, which is 0. Okay. So what does this mean? We've got these two values here. What do these values of dv dt mean? What does this dv dt of 0 mean? So at 10 seconds, the rate of change of volume with respect to time is 0. So what's happening? The sink's not draining. So there is no change in volume at this time. Kind of like it's stationary, it's stopped. Sink's no longer draining anymore. What about this value of negative 800? What does that mean? What units would you use here? We're draining out at negative 800. What units? Millilitres per second. Per second. That means every second we're losing 800 millilitres of liquid down the sink. It's draining pretty quickly. Okay, guys. Alright, now let's have a look at a little bit trickier one. Oh, I'm just going to cover these up for a minute. Alright. We have a function pt which approximates the blood pressure. We've got p millimetres of mercury at time t seconds. So our quantities that are being compared, we've got the blood pressure of p millimetres at time t seconds. Right, so find the initial rate of change of blood pressure. Okay, let's have a look. We've got rate of change, that's an important thing. So this is a function showing the blood pressure at any time t. Oh, let me just get rid of one little thing there. Oh, where are we? That pi is not supposed to be there. There we go, just t over 2. Okay, so the first thing we're going to have to do is find our rate of change. What are we going to call it here? If our function for the blood pressure p millimetres is pt, it'll be the best thing, call it p dash t. Alright, we've got a nice trig function here, so let's do that. 100 differentiates off to 0. Negative cos function, well, we've got negative 20, our coefficient. What does cos differentiate to? Cos differentiates to negative signs. We've got negative 20 times negative sine of t over 2 times, remember the derivative of this function. What's the derivative of t over 2? That's a half. Okay, so let's neaten this up. We can got some negatives here. I think we end up with, cancel that out there, we got 10. 10 sine t over 2. So here's our rate of change. So what do we actually want to find now? We want to find p dash 0. So we want the initial rate of change. Well, let's put that in there. We have 10 sine 0 over 2. 0 divided by 2 is 0. What's the sine of 0? I always like to think of my little sine curve there. Sine of 0, 0. So we have 0. So the initial rate of change is 0. That means at 0 time the blood pressure is not increasing or decreasing. It's changing. But that might quickly change. Find the longest time period for which the blood pressure is increasing. Well, there's a few ways we could do this. Alright, let me get rid of this. I've got a few graphs down here. This first one here is PT. So we've got T and PT. I've graphed PT equals 100 minus 20 cos T over 2. So we can have a look at this. Find the longest time period which the blood pressure is increasing. So we can go and have a look at our graph. Where is it increasing? Certainly going up here all the way up to there. Okay, so we want to now find what this value is here. So let's go to our calculator. Where are we? Oh, that's not the one. Alright, here we go. I can go over here and I'm going to find this value here, because then this period is the largest period we have where the blood pressure is increasing. So I'm going to find the value of x where we have this maximum here. Come over here. So I'm going to go, I can't see this very well on the screen, second calc, and I can find the maximum value here. So left bound, we're on our left bound, yep. We're on our right bound there, guess. Let's see, we have this value here is approximately 5.8 seconds. So from 0 to 5.8 seconds, we have an increasing blood pressure. That's one way we could do it. We could also think about this. If you have an increasing blood pressure, what do we know about the derivative? This is a graph of the derivative here, T and P dash T. What do we know about the derivative? When you've got an increasing function, have a look at the slope of the tangent here. What do we know about P dash T over this interval? P dash T has got to be positive, hasn't it? It's got to be greater than 0. So let's have a little look over here where it is greater than 0. Well, here's our PT axis. Here, it's greater than 0. It's decreasing here, but it's still positive, isn't it? It's still greater than 0. So once again, we come down to this same point. This point over here, once again, approximately 5.8 seconds. So we could use the graph of the derivative and where the derivative is positive. Now the last one I've got here is the second derivative, P double dash T. Okay, what do we know about the second derivative? We want to see where the blood pressure is increasing. What do we know about the rate of change to P dash T over this part where it's positive? What's happening to P dash T? It's decreasing. So we want to have a look at P dash T and see where it is decreasing. So let's go over here. If we start here, okay, it's positive, but it's decreasing all the way down to here. Okay, so at this point here, once again, 5.8. So if we were using the second derivative, we could find where p dash t is decreasing. So this is where all our knowledge of first and second derivatives and things come in. So all of those fit together. Where our blood pressure is increasing, just a simple look at the graph, it's going up. If we look at the graph of the derivative, we want the derivative to be positive because we have a positive slope of tangent over here. So there is our derivative being positive. And if we've got a maximum here, we know we have a decreasing second derivative. Okay, so there's a couple of examples that I'd like you to have a look at. Be ready to talk about these in class next time. Okay guys, see ya.